Good morning, everybody. Today we have better audio than last time, so we should be good there. And we also have Div 1, Div 2 round combined. This is the Latoken round. A minute late because I had some camera issues, but here we go. Alright, we're playing a red and white coloring game. You're given an N by M grid, RW, and period characters. The neighbors are things that share an edge. You want to color the blank cells red or white so that every cell has white neighbors and not red ones. Oh, every red cell has white neighbors. Every white cell has only red neighbors. Okay. Yeah. So we're given height and then width. Boolean. As usual, solutions will be available at the end. And there won't be quite as much commentary this time, because it's rated for me. This is not equal to a period. So both ways, since this out, no. Alright, yes, oh yes, okay, start with W, start with R, looks good. We should be fine there. Oh man, are we gonna TLE on problem A? Small test case is smaller grid, we should probably be fine, we'll see though. Alright, so we got it. Problem B, histogram ugliness. Little Dormy received a histogram with n bars of height A1 to AN for Christmas. However, the more he played with this new histogram, the more he realized its imperfections. So he wants to modify it. To modify the histogram, he is able to perform the following operation. Select some index and subtract 1 from it. He defines the ugliness of the score of his histogram as the sum of vertical lengths of the outline performed on it. So 1, 2, 3, 4, 5, okay. The blue region If he does not modify the histogram at all, it's 18. On column 2 twice, and column... So decrease this twice and this once, and then you have it up. Yeah, okay. So you've just decreased it by 3. 1, 2, 3, oh, by 4. So it goes from 18, initially it was... So initially it was 18. Oh, gotcha. So he decreased it by 3. Yeah, okay. So the question is the minimal ugliness you can get. So you just want to decrease if it's 1 tall, you want to decrease it because then you get free stuff. If it's 2 tall, it doesn't matter. So if it's taller than both of your neighbors, you decrease it to one of your neighbors, and then you get that many things for free. Yeah, okay. Let's try that real quick. So we'll read in the array with some padding, and then this is the initial thing. Okay, and then long sub equals 0. N is big, so we need a fast scanner. Do we need print writer? Probably not. Yeah. Let's read C while we wait for our results on that. Well, he's not training for IOI. Alan enjoys puzzles with various types. Sorry, so we got it. Nice. Of various types to stimulate his brain. Today he's playing a puzzle that consists of a 2x(n) grid where each row is a permutation. The goal of Alan's puzzle is to make sure no numbers in the same row, no numbers on the same column or row are the same. So each row is already a permutation. You need to make each column a permutation. To achieve this, he's able to swap the numbers in any column. What? He's playing with a puzzle that It's a 2 by n grid. What does that mean? Height 2 width n? Yeah, they do height width usually. So you have like 1, 2, 3, 4, 4, 3, 1, 2 maybe. He wants to make sure no numbers in the same column or row are the same. He's able to achieve this by swapping the numbers in any column. So you have like a pair you can swap. However, after solving this many times, he got bored and began wondering about the number of possible solved configurations of the puzzle he could achieve from an initial solved. Oh, it's initially solved. Yeah. What? So you've got 1, 4, 2, 3, and 3, 2, 1, 4. Oh, gotcha. So you can swap. So you can have 3, 2, 1, 4, 1, 4, 2, 3. Oh, you can swap all of them? Okay. Yeah. But you can do more. So you have some groups. I think this is going to be a power of 2, right, for each group. So in this one, you have, let's do it here. Yeah, so you've got two, 6, 5, 1, 4, 3, 7, 8, 3, 8, 7, 5, 1, 2, 4, 6. So this needs to include the 2, which includes the 3. So this is one group. Okay, next group we have this 6 and 8. So it includes these 2. Okay, and then we have green. So 5 needs to include 7, and it also needs to include 5. This needs to include 1. This needs to include 4, which is in this group. Yeah, so we have 3 groups, so it's 2 to the 3. Yeah. Okay. Good. Let's implement it. Okay, so then we need the index of each thing. And then same thing here. Alright, so now we have a bunch of things. We have their indices. So now we need the number of groups. So and then we have 4 equals 0, less than n, plus plus. So if this thing is not hit, well, if hit at I, then continue. So we need an array, dec, integer q, array, dec, while q that is empty. We'll say n groups plus plus, hit at I equals true, q dot add I. Next equals q dot remove. Okay, so now int array to check equals a1 at next, a2 at next. All right, so now int array others. Well, okay, so now for int I and to check, int position of canned equals index of 1 at canned, and then index of 2 at canned. And then we say q dot add other position. Alright, I think that's it. So we should be good to go there. 2.8 looks good. Oh wait, is there a lot of output here? End of the floor. Should probably be fine. Okay. Let's move on to problem D. Voice crack. Interactive problem. Yeah, they warned about this in the problem announcement, so we'll see. Little Dormy is faced with an awkward problem at the carnival. All right, we got it. He has to guess the edges of an unweighted tree of n nodes, exclamation point. The nodes of the tree are numbered from 1 to n. The game master only allows him to speak one type of question. He gets to pick a node R. The game master will reply with some array where di, so he picks some node. This is the length of the shortest path from this to this. Okay. Additionally, to make the game a challenge, Little Dormy, the game master. What? Oh, to challenge Little Dormy. The game master will allow at most n over 2 ceiling. This is a lot of interaction. Okay, so, well, what do we print? Print all the edges. All right, so let's think about this for a minute. If we're given like some nodes, we know these are all distance 1. And we have a bunch of nodes that are all distance 2. So one thing we could do so here's what we do. So we two-color the tree like this, and then we can initially we can find everything's color from the beginning. If this red is less than or equal to half, then we query all red. Otherwise, that means green is less than half. So we query green. Okay. yeah, so we are given n. Wait. Query node 1 as the distance over there. Okay, yeah. All right. So this is D. This is distances. Okay, so we need even count equals 0, odd count equals 0. If distances I mod 2 equals 0, then even count plus plus. Else odd count plus distances at I equals 1 is edge from 0 to I. This is edge from I to 0 equals true. If even count times, well, if even count is greater, less than or equal to n plus 1 over 2, do this, otherwise do odds. Okay. So then for each thing, this out, question mark plus I plus 1, and then array dist equals fs dot read array size n. If dist at j is equal to 1, then is edge at j I equals is edge at ij equals true. This out, exclamation point, and then so 1, oh, I guess let's do it better. Oh, it went 2, okay. 1, 2, 2, 3, 4, 2. This is kind of impressive. I just got this right, I guess. Cool. Try submitting. We can test it more if we don't get it. I guess that's not the right strategy, but is 14. All right, looks like we got it. All right, moving on. Moving swiftly along. Problem E, XOR. I love XOR problems. Watch me. Oh, another. Oh my goodness. When they said at least one interactive problem, I didn't think they meant it so seriously. Woohoo. All right. Notice the XOR sum of some array is the XOR of the array. Okay. Thank you very much. You've got an array of n integers for Christmas. Oh my goodness. Usually it's for your birthday. What an upgrade. Okay. When playing with it over winter break, he accidentally dropped his XOR machine and the array got lost. Uh-oh. You're in trouble now. The XOR machine is currently configured with a query size of k, which you cannot change. Allows you to perform the following type of query. Given the machine k distinct indices, it will output the XOR of these k things. As his older brother, you would like him to recover the XOR sum of the array by querying the XOR machine. He isn't very patient, so to be as fast as possible, you must query the machine the minimum number of times to find the XOR sum of the array. Let this be the number of queries. Your program will be accepted only if you do it in d queries. Lastly, you notice that certain configurations of the machine, values of n, it may not be possible to recover the XOR sum. If this is the case, you should report it as well. Ends up to 500. Okay. Thinking time. Put on the thinking cap. So yeah, that's a thing. But we don't know this. So if it's a factor, that's easy. Five, 3. 1, 2, 3. 1, 2, 3. Well, 1 isn't impossible. 3, 2. Sorry. Google is giving me a bunch of notifications for some reason. Okay. Why? So 1, 2, 3, 2, 3, 5, 4, 1, 5. So we know this one because it's only included. Well, what the heck? So you're saying we can hit everything here? I don't know that this is actually a legit strategy. So that's a thing. Huh. Okay, what if k is 2? What happens if k is 2? Well, if it's in even length, then it's easy. If it's not even length, it's like 5. You get the XOR of pairs. Yeah, so then you have a graph with some edges. But you can change this and it'll change everything, so it's not possible. What if k is 4? Well, if k is 4, you could solve it from 2. So when k is even, then the answer is no, if it's not a factor. If k is odd, nine and 3, then we can do, what if n is even? We have 12 and 3. Well, then it works because you do everything once. One, 2, 3, 4, 5, 6. Yeah. Okay. What about something else? What about 3 and 4? So you can do 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, I guess you'll always hit this. This will happen 3 times, right? And then the number of queries equals n. Okay, what if they share a factor though? So what if it's something like, okay, if they're coprime, so we have the factor case, we have the coprime case. If they're not a factor, they're, well, coprime, and also k is odd. Not a factor, not coprime, then what? What's an example of 2 numbers where, okay, so pick some odd number, David. Pick some odd number with multiple factors. An odd number with multiple factors. 15 is the smallest one, right? 3 times 5? Ugh, so big. Okay. So we have 15. And then we need something that isn't a multiple of 15 but shares factors with it, like 20. So you divide out the GCD. It's the same as 3 and 4. So then you take 4 turns. Okay. We can try it. Is it right? Who knows? requires some mathematical proving, you know? And I don't know how to do that, so let's just throw our hat in the ring, see what sticks. I guess let's look at the standings, see how many submits there are. Okay, so about 50% success rate. Not terrible. Yeah, let's try it. One test case, int n, and then k. Okay, so okay, if n mod k equals 0, then this is easy. I guess this is also the GCD case. So if k mod 2 is equal to 0 and n mod 2 is not equal to 0, then this is out impossible, I think. We'll try that. Okay, otherwise, in GCD between the two. Yeah, so then we want Alright, so start equals n times, or equals, I guess, k times I modulo n. These are both small. Okay, that's fine. So then for an offset equals 0, offset is less than k, offset plus plus for int d. Okay, so now int to print equals start plus offset. So then we want scale up by GCD. So now for int GCD count, or GCD offset equals 0, GCD offset is less than GCD offset plus plus. This out to print times GCD plus GCD offset plus a space. Okay, after we print this, we get some input. After we print this, we get the XOR. So the array is 2, 1, 7, 5, 6. So let's try this. 1, 2, 3. So let's do these in binary. So 2 is 0, 1, 0. 1 is 0, 0, 1. 7 is 1, 1, 1. 5 is 1, 0, 1. 6 is 1, 1, 0. Okay. So 2, 1, and 7. So we have 1, 0, 0, which is 4. Oh, there are 5 numbers. And then k is 3. Okay, that's wrong. Plus 1. Oh, so this needs to be mod n. Mod n, and this needs to be plus 1. One, 2, 3. Okay, so this is 4. Okay. Do these need to be in ascending order? Yeah. 4, 5, 1. So the XOR of these is 3. XOR, so it's 1. And 3 or 2, 3, 4. So the XOR of these is 4. So the answer is 3. 5, 1, 2. 6 flip 3 would be 5. 3, 4, 5. So that's 2. So it's 4. They're saying it's 7. Okay. Well, that means each bit is an odd number of times. 1, 2, 3. Middle one, 1, 2, 3. Yep. Plus 1, 1, 2, 3. Yeah, so is the answer 7? Yes, it is 7. Okay. We can try it. I guess let's try multiple too. So let's try 2 or 4, 2. 1, 2. The XOR of these would be 3, maybe. 3, 4, the XOR of these is 3, the answer is 0. Let me go to the bathroom, I'll be right back. Aha! Wrong answer, pretest 1. Alright. Why is that? Because we used too many queries? Oh, you can do it in 3. You can do it in 3? Okay, how do you do it in 3? So 1, 2, 3. Oh. Yeah. Okay. Got it, got it, got it. So okay, yeah, I see. So you can, got it. So you can do, I think any even number, you can erase any even number from your answer. Okay, so we've, good. So we've actually proven this. Okay, so let's actually prove the answer here. So if one's a factor, that's easy. Okay, if otherwise, if k is even, then the answer is no. K is even and n is odd, you're never gonna, like, yeah, you need to use, yeah, it's not possible because you just have a bunch of edges in a graph. You can't do it for an odd-sized component. Okay, all right, so the last one is we have n over k plus, well, n over k ceilinged. Might that work? You can subtract an even number here. So we can do 1, 2, 3, 0, 0, 1, 2, 3. So now we have an overlap of 1. So we have 1 too many. So if k is odd, we need an odd number of queries. Do we? Yeah, we need an odd number of queries. So what if we have something like 5 and 9? 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, but then we have a problem, so you can't do this. So five and 9. So 5 and 9 takes 3. So you have 4 remainder, or 4 left, and then you split them into 2 groups. Okay, what about something like 5 and 14? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then we have 1, 2, 3, 4 left. Well, it's possible in 4 queries. So we don't need an odd number of queries. Yeah, that's just not the case. This takes 4. Yeah, okay. So is it ever not ceiling plus 1, I guess is my question. What about 11? Five and 11? Yeah, so 5 and 11 is 3. 5 and 14 is 4. 5 and 13, I think, should also be 3. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then we have 3 left over. So then we do 1, 2, 3, 4, 5 here. Well, okay, this is the wrong way of doing it. So 5 and 13, so we need 5 over 13 ceilinged. Well, yeah, so 5, 13 over 5 is 2 remainder 3. So if we do 3, then we have 2 left over, 2 extra, so we're good. We're okay. All right, so we have 2 extra. So we have like 1 extra space that we do 3 times. We have 1, 2, 3, 4, 5, 1, 6, 7, 8, 9, 1, 10, 11, 12, 13. Okay, I think I have an actual answer here. What if the parity doesn't work out? So what if it's something like 12? 12 over 5 is 2 remainder 2. So if we do 3, then we have how many extra? If we do 3 5s, we have 3 extra, but that's not possible. So if we do 4 5s, then we have 8 extra. That means there are 4 groups. So we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, okay, I think that's the right answer. Okay, so let's do E right. this is the case, then we print, yeah, then this is easy. Oh, what if they're both even? Yeah, so you can divide out the GCD. So we do need the GCD. So we have the GCD of the two of them. So now if k mod 2 is equal to 0, this out -1. Otherwise, it's possible. So then we print each of these, and then ants XOR equals the next int. And we print the answer at the end. Okay, good. So now, if k is even and n isn't, there we go. Okay, so now we're in a static. Int query int x, or I guess an array list. So then we have this, and now we need to print each of these things. So for int I into query, int I, or int GCD offset equals 0, GCD offset less than GCD. So I times GCD plus GCD offset. that's right. Okay. So int min times would be, okay, so we need the number of times. And, number of queries is equal to n plus k minus 1 over n over k. Alright, so in total things, well, okay, so int extra would be k times n queries minus n. If extra mod 2 is not equal to 0, then n queries plus plus in extra equals k times n queries minus n. If extra mod 2 is not equal to 0, then the row null, which should never happen. Alright, so now we need an array dec integer okay, so oh, is this gonna be a problem? What if, yeah, no, this should be fine. So we need a last picked. Oh, we also need how many to skip. Okay, so now we say toQuery.add toQuery.add I. Turn is less than n queries. If turn is less than 3, do this. Okay. And then ants XOR equals query GCFS. All right, 3, 5. Nope. 5, 3. 1, 2, 3. That's 1. 1, 2, 4. It's 1. 1, 2, 5 is 1. The answer's 1. Yeah. Okay. What if we do something else? What if we do 4, 2? That's wrong. Okay. That's why we test this plus a space. 4, 2. 1, 2 is 1. 3, 4 is 1. Okay. Let's try it. Oh, we should have. I had some good cases here. Let's try them here. So 5 and 12. Nope. 12 and 5. So that's 1, 1, 1, 1. Yeah, okay. 13 and 5. 1, 1, 1. Wrong answer, test 4. Are we too big? Or too small? I guess I didn't try anything with the GCD. Eight and 4 or 8 and 6. Okay, that would be wrong. Yep, that's wrong. Okay, what is 8 and 6? 8 and 6 is really 4 and 3. So let's try 4 and 3. 1, 2, 3, 1. That's not right. What the heck? So you query 6 things. That's what we're trying to do here. Okay, so really you query 4 unique things because you waste 2 turns. Or any queries less than 3. That's not even the right number of things. What am I doing? What? Okay, how do you do this? Is there an easier way of approaching this problem that isn't constructive? we get a dp of n even equals a min number of turns. And even and odd, I guess. And your transition is try taking each number of them. That's annoying. Do I have a better chance at doing something else? Yeah. So dp is number even, number odd. Transition is k. Yeah, okay. Alright, so this gets handled, then this part is what we need to actually do. What if there are transitions in this? Or cycles? Okay, so instead we need a graph. N even by n odd. Then we do a BFS in this graph. Is n by n, right? What's our time limit? 1.5, so tight. This might be too quick. Yeah, okay, so we have some number of even things, some number of odd things. I guess we just do this the right way and then pray that it runs in time. Just so you have n is 0. Oh, there aren't actually that many nodes. Yeah, there are only n of them. Equals new int array, or equals 0. Array deck integer. So this is n even equals dfs.remove, and n odd equals n minus n even. Okay, then for int to remove, or int n even, I guess n odd to change equals 0. Number of odd things we have, and k, n odd to change plus plus. And n even to change would be k minus n odd to change. And other node would be n odd plus n even to change minus n odd to change. So this is n even minus n even plus number of odd. Okay, so So now we have this thing. Okay, and then n odds changed. Back to the n. Add n odds changed to get here. Add. All right, good. So we should be fine here. So now, even dot add I. Alright, array query array list and evens change statements and odds change. so update this, make this even, or make this odd, and then to query dot add make odd. Okay, now we just need to do the same thing backwards, and odds to change. We want to make this even. Okay, so good. So now we have all of this. We've changed the things. We need to query this stuff. I think that part of the code should be fine. Okay, do we still have our answer somewhere up here? Yep, okay. So now we say ans XOR equals that, sys out the answer. Okay, lots of stuff, but I think we're fine. So what does 4, 3 look like? 1, 4, 1, 2. Yeah. 1, 3, 4. 2, 3, 4. So 2 is used 3 times, 1's used 3 times, 3, 4. Okay. I think that's the best. All right. Do we need any of these special cases even? Probably not. This should just handle everything. Yeah. So I think we can just do this even. Oh. Well. Let's just submit it. Running on pretest. Which pretest? Oh boy. Be right back. Gotta go handle something. That's kind of annoying. Might be this case. Might be getting killed by this. Alright, be right back. So what could be wrong here? Is it possible to do in fewer moves? I guess it's possible this isn't the case. Part we shouldn't need. And this part we also shouldn't need. You should just be able to be 1. If you get like 2, 9. So we've got that. I wonder if this fixes it. Let's look through this part just once more to verify it. So we have how many even there are, how many odd there are. Okay, so this is the number odd we want to change. Less than or equal to either how many odd there are or k. Number of even to change is k minus how many odds. So it's always positive, but it might be bigger than how many evens we have. Number of odd to change is always legit. Other node would be number of even minus number of even to change plus number of odd to change. Move first, add last, add last. I wonder, yeah, I don't know what the problem here is, but it would be nice to verify it's in this part of the code. Can we write a brute forcer for this? Maybe. We can make a randomized input, because input is only dependent on two things. Okay, I don't understand this. How does the queue get longer, like 2 hours into contest? There's certainly less submissions. There've got to be. Right? I don't know. I feel like most people are submitting right in the beginning. Because you got like lots of easy problems all at once. Or maybe not. Maybe people are getting frustrated now and just submitting. Can we see what this is on, please? Oh my goodness. Really? Okay. Well, good thing we tried that. Simple code for the win. I really don't know what the bug was, but could have been a GCD related thing. Interesting. Alright. Cool, cool. So F1 looks like the play. Alright. So the difference between this version is the constraints on AI. He received a puzzle from his friend, needs your help to solve it. It's an upright board with n rows and m columns, some empty and some filled with blocks of sand. M non-negative integers, a1 through am. In this version of the problem, ai will be equal to the number of blocks of sand in column I. Yeah. When a cell is filled with a block of sand, when a cell is filled with a block of sand is disturbed. When a cell filled with a block of sand is disturbed, the block of sand will fall from its cell to the sand counter at the bottom of the column. When a block of sand is falling, other blocks of sand that are adjacent at any point to the falling block of sand will also be disturbed and start to fall. Okay, in one operation you're able to disturb any piece of sand. The puzzle is solved when there are at least AI blocks of sand counted on the ith counter for each column. Minimum number of operations. Okay, what happens here? So we need 411103. So this one, this one, this one. Hits everything. Why everything? Okay, so in this you need to make everything fall. Okay. So it goes down and activates everything around it. Block of sand will pass through all cells below and including this cell, disturbing all adjacent cells along the way. Okay. Print the minimum number of operations needed to solve it. Okay, so each thing has, you have like a directed Yeah. So you've got like a directed graph of things which hit you. How big is this board? Up to 400,000. Okay, so if you have like a piece of sand and then a block and then a piece of sand below, that can reach that, but it can't go backwards. The sand blocks do not stand on each other and do not prevent each other from falling. It falls independently of whether there's sand block underneath. Yeah, I think I understand. So a block will hit everything in like some range, which we can calculate in order 1. So we can make this digraph. And now the question is, what's like the minimum number of nodes we have to hit that will erase everything? So if we make the digraph, and then we run SCCs. If we run SCCs, what does that tell us? That tells us if you hit any block in here, that it'll all fall. We run SCCs, and then we want the number of SCCs with in degree equal to 0. Yeah. Because you can't have a cycle of SCCs. Okay. So that's the solution to this small version. Do we want to just do that? Probably. Yeah. I guess we can. This is height and then width. Okay. Per board. Good. So now, yeah, I guess int ID, new int width by height, int n nodes equals 0. So we can do this from bottom to top, I guess. Int y equals height minus 1, y is greater than 0, y minus minus. Equals 0, less than width, x plus. If board xy is not equal to period, then ID at xy equals n nodes plus plus. Alright, so we have that. So now we need to assign adjacency. So we need SCCs. What's the time limit on this problem? If they give me a tight, I'm gonna go insane. Okay. SCC. You people and your tight time limits. I'm getting sick of it. Okay. All right, so we need SCC and nodes. All right, so now we need the top in each thing. Okay, so int array top in x equals new int array width. Arrays.fill top in x with -1. Yeah, so now do this. Okay. ID x -1. Just in case we do something bad, then we'll know. So we fill, okay, so we do this. So now, if this is the case, then top in x at x equals ID at x, y. This at the end. So now we need to add some edges to some stuff. So if top in x at x not equal -1, then SCC dot add edge from ID at x, y to top in x at x. If x is not equal to 0 and top in x minus 1 is not 1, then add top in x minus 1 and okay, we're almost done here. So this is x plus 1. This is going to be a bit more messy. So if x is not equal to width minus 1, do some stuff. So if board at x plus 1 y, then we need to scc.add ID at xy to ID at x plus 1 y. Otherwise, we need to do this. If the top is not equal to -1, then add the top. Okay, I think that's all right. Good. So now what do we do here? Then we update the top, and then we also need the thing above us. If y is not equal to 0, then board at x, y minus 1 is not equal to a period, and scc.add ID at xy to ID at x, y minus 1. scc.go. scc.compress scc. New graph that all SCCs compressed into one node. Yeah. Okay, so we have this. Now we need to count. All right, so count equal Boolean array as in equals new Boolean array count dot size count dot length. B. If it doesn't have in degree, then count plus plus. Seven. For real? Okay, 0, 4. Adding edge, 2, 4, 0, 3. Add an edge above, add an edge below. Okay. Zero or 5, 3. So this one, add an edge above to the right. 6, 3, add an edge to the left. 0, 2. Add an edge below. 5, 2, below and right, so this looks fine. Do I have my numbers right here? -1, +1, +1, I guess let's do this one here. These are all in one SCC. This is in another one. All right. Oh, has in equals true. I'm an idiot. Okay. Yep, looks good. So question number 1, do we get Java on this? We just print one number, so that's fine there. Print writer, let's try it. Alright, I'm gonna go to the bathroom. Hopefully this figures itself out. running on pretest still. Okay. Oh boy. Oh boy. Oh, 2 second timeline. Alright, we're fine. Okay. Well, what do we stand a chance at getting? So in this case, you still only want to hit the root nodes of an SEC. Nothing else matters. The problem is you just might not need to hit everything. Yeah, you would never want to hit not a root node of an SEC. You could just hit a root node instead. So you're going to hit some roots. Additionally, there's only one root per row. Right? Yeah. Yep. Alright, so this is a thing that we might be able to solve. I guess let's read this. Choose peat and potatoes to plant. Yeah, must be planted at this point. Starting at point 0, 0, she begins walking. In one step, she can travel 1 unit right or up. At any point during her walk, she can plant some potatoes at arbitrary points using her potato gun, consuming the maximum of the difference in energy to plant a potato. Find the minimum total energy required to plant every potato. What now? Oh, she takes some path. Yeah, okay. So you have a bunch of points, and you're going to take some path, and you want to minimize the sum of distances to each thing in the path. Okay. Three interactive problems. My goodness. He's very bored, so he decided to play a game with this new tree. He selects 2 nodes, then gives him a hint. Some node on the path from A to B. Then he's able to ask the following question. If I root the tree at R, what would be the LCA of A and B? Oh, he selects 2 nodes on the tree and then gives him a node on the path. They're all fixed before the start of the game, don't change. Although I don't really know that you can rely on that too comfortably, because it's not really that much randomness. So n-1 times, you pick some edge, maximum number of queries. So it's like, what's the minimum number of, okay, so I guess it's just how do you do it, and then once you know how to do it, you have to do some other observations. Yeah, maybe centroid decomp or something. So for F2, only consider the top node in each column. And then we want to say something like well, we would need some sort of DP. We pick a monotonic chain. Is there a monotonic chain that's interesting? So like if A has a path to B, and then B has a path to A, then they're in the same SCC. Yeah. So let's say we sort the SCCs from left to right by highest node. What does that help us do? So now we know that, yeah, now we have like some ordering. And then we can say dp at x So for some node, which SCCs can hit it? Well, the one above it might be able to. It's going to be a continuous range of SCCs. A continuous range of SCCs will be able to hit some node. Oh, also, yeah, so the way this works now is that you now just have some nodes which are optional. So now you have some mandatory nodes and some optional ones. Got it, got it, got it. I guess you can't do this with a general graph though, because it's like min vertex cover. So you have to abuse the fact that this graph is like very linear. So for some, yeah, for some mandatory node, there's a continuous range of SCCs. That hit it, of like max SCCs. So you need to pick one of those at least. Oh, is that it? Hold up. if we know which SECs hit it, if we know which SECs hit it, then it's just guessing bunnies. Alright, so we're making some progress here. So let's get another sheet of paper, do it from scratch. Okay, so we've got, so we're gonna sort SEC, well, okay, so yeah, sort SECs by the X of highest node. Okay, sort the top SECs, the ones with no integrity. So now we have a sorted list. So then we want to say every required node has some range of SECs. Okay. So then, yeah. So now we want to see the leftmost and rightmost, or oh, what do we need? Like we need to see, can some SEC reach me in the SEC tree? And then, so then we binary search to the left, and then right, and then we do guessing bunnies. Okay, so so we need int ID, and then we need int X. And then I guess an int Y too. All right, so as less than comp, or as less than as in length plus if has in I, then top SCCs dot add new top SCC I. Okay, so now we need to update the ID of the highest thing in each SCC. Sort by that. so if it's a period, continue. So then otherwise, it's not a period. If not has in degree at map at ID of x, y, then int, okay, so then we need to actually get it. Top SCC array, all SCCs by index. Okay, then equals all SCCs by index at I. Alright, yeah. Okay, so now top SCC, my SCC, oh, I guess, yeah. So if, okay, and not has, oh, so this means, yeah, so then I am part of a top SCC. So then we top SCC my SCC equals all SCCs by index at map at ID at x, y. Okay, so this is my SCC. So if okay, so now we need y equals integer dot max value. So if my SCC dot y is greater than y, my SCC dot y equals y, my SCC dot x equals x. Okay, now we need to arrays or collections dot sort top SCCs. All right. Now we need something here. So now this is a tree. So now we need the pre-order and post-order in this tree. Right? We need to know if one thing can reach another. Oh, is it a tree? It's a digraph. Has no cycles. So we need to know, can one thing reach another? Yeah, we need to know, okay, we need to know which things an SCC can reach. So, well, we need to know the leftmost and the rightmost thing it can reach. Right? We need to know leftmost and rightmost. Leftmost and rightmost extreme point? That's not... Yeah, that's not right. We need to know the leftmost and rightmost. Leftmost plus rightmost top SCC that each node can reach on reverse edges. Minutes. Oh boy. Don't think I can do this in 30 minutes. So we have this. Yeah, so we need to know the leftmost and rightmost node. Oh wait, that's easy though, because we just reverse these edges, and then do it in top sort order. Yeah, because this is on SCCs. Yeah, I might actually be able to finish this. Okay, so, okay. Top SCCs. I guess. Okay. Rev comp at j. Okay, so we have the reversed graph here. Okay, so now we need the in degree of each thing, or we need the out degree. Okay, so now 4, 0, so rev comp.length plus of degree I equals order. Okay. Yep. So if out degree I equals 0, then BFS dot add I. Okay. So now, while not BFS dot is empty, we also need for each thing, for each SCC, we need the leftmost and rightmost it can reach. Okay, so yeah, so we need int array leftmost can reach is new int array ref comp dot length rightmost can reach equals, I guess this is a top SCC. New top SCC array rev comp dot length. What do you mean? Top SC, yes I can. I resolved it myself, right here. Boom, you got it, come on. Eclipse, you can do it. Stop freaking out on me, it's a rated contest here. Chillax, okay. Oh, new, thank you. Okay, yeah, gotcha. So, so now this is int SCC process equals BFS dot remove first. So now for int can reach in rev comp at SCC to process. So if not has in at SCC to process, then this is a top SCC. So then leftmost can reach at SCC to process equals rightmost can reach at this equals me. Equals what I call these, all SCCs by index at SCC to process. Okay, so this is what happens if it's a top SCC. What if it's not? Okay. So now leftmost can reach at SCC to process equals left. What do I call this method? Left of leftmost can reach at SCC to process, or this one right here. So or leftmost can reach at can reach. And then we do the same thing with rightmost. Okay, so yep, we can't have two SCCs that both reach each other. Good. Okay, now we have to update the BFS. So now for int I in comp at SCC to process This is all the forward edges. So now degree, out degree, at I minus minus, if out degree I equals 0, then bfs.add last I. First, okay, so we're doing this. Okay, so now we have the leftmost and rightmost thing each one can reach. Wait a minute, now all this is yeah. Okay, now we just need to build these ranges. Okay. So now we need a static class bunny range. Implements comparable. How much time do I have? 20 minutes. So int lr public bunny range. Int l int r. This dot l equals l. This dot r equals r. Public int compared to bunny range o. We want to sort by right endpoint, right? I think so. All right, so now we need to build all bunny ranges by the restricting nodes. Alright, so array list, bunny range, ranges, new array list. Okay. I didn't even read in bottom input here, but now I need to. So this is width long. Okay, so int array requirements equals fs start read array width. So now for int I equals 0, less than rex dot, or less than width I plus plus. We'll call this x. If rex at x equals 0, then continue. Otherwise, for int y equals height minus 1, y is greater than or equal to 0, y minus minus. Okay, so if board at xy is not equal to a period, then rex at x minus minus. If rex at x equals 0, then we need to process this. So now okay. So int sec will be map at id at xy. Ranges that add new bunny range from leftmost can reach at my sec dot sorted order to rightmost can reach at my sec dot sorted order. Okay, so we're done with that. Arrays dot sort bunny ranges, or sort ranges. Collections, rather. Yeah. Wait, how does, oh my goodness, am I an idiot? How does gassing bunnies work? We sort them by their left endpoint. Yeah, sort by left endpoint. Okay, so this needs to be compare left to other left. All right, so we sort the ranges. Now we have the count. So now 4 bunny range are in ranges. Int last kill equals I can't be this bad at programming. This doesn't, nope, does not work. Okay. We sort by left endpoint. Wait, okay, so it's we kill bunnies, we wait as long as possible to kill a bunny. So we wait until the right endpoint is about to end, and then we kill. Yeah, so sort by right. Or do we want to sort by left? Ah, okay. So if we sort by the left endpoints, then yeah, no, okay. So instead we sort by right. We store the last kill. Sort by right, store the rightmost kill. Yeah, okay. All right, equals integer dot min value. Sort by right, and then where was I? Okay. So if last kill is greater than or equal to r dot l, and continue. So already dead. Otherwise, I'm the most restrictive alive. So kill my right. So then otherwise count plus plus last kill equals r dot r. Okay. Okay, so the ranges are broken. Yeah, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we got one part right. Yeah, so does this part work at least? So 0, 0, 1, 1, 2, 4. Yeah, that's right. Okay. So we've got that working. So now, so 7 SCCs apparently. 0, 1, 2, 3, 4, 5, 6. Okay. Okay. So each of these are false. Okay. So these look different. Okay. Oh, we never set the sorted order. Yeah, so top SCCs. Oh, top SCCs, that size. Space. Three. 1. 1. Okay. Let's try submit. Disenchants me TLE here, which would be really annoying. What do we do in that case? I wonder if the first 30 pretests are the same. Possible. Looking somewhat promising. There we go. Somehow faster. All right. Good. That's my contest, ladies and gentlemen. I'm happy with that. We beat a Python user. This TLE? Oh, wrong answers. Okay, annoying. Wait. Oh, Conqueror Tourist doesn't have F2. Okay. Interesting. Yeah, so GG. That was fun. I enjoyed that. It's a fun contest for me. Yes, please. Give me my delta. Maybe. Is it plus 43? It might be. It might be more, though. I'd be happy with a plus 43. Yeah, sounds good. What would plus 43 give me? It would give me... I wouldn't get IGM back, but I'd be not terrible. Is it plus 43 or has it updated yet? It might not have updated. I don't know. We'll see. We'll see in 7 minutes. So now my question is anything being hacked? Do you go to those? Because we definitely don't have time to solve anything. Any hacks? No hacks in my room. What about in the common standings? Well, how many people are even in my room? It's a small room. Okay. We got some bad people. But what is A? Yeah, this thing. Okay. What about in the common standings? Is anyone getting any hacks? one hack. What is this hack on? Hack of A. All right. So let's double check A. Yeah, okay. So I guess what's the case if we do like 1 1 dot what? Oh, 1 1 1 dot R. Okay, maybe that's the case. So, oh, can we see? Can I see this? The samples? No. All right. Yeah, let's try it. So. Okay, we got some stuff. DFS, what? It's actually called? Oh boy. Okay. How on earth do you have code this complicated for this problem? Okay. So test plus plus, read in N and M. You got your vector, you read it in, dot equals true. So dot is there any non-dot? Or I guess dot means all dots. Okay. So if it's all dots, do this. Is this case right? What? W. Oh, he flips it. So it goes red and J mod 2. Yeah, okay. I think that part's fine. It's very messy. If some stuff, DFS, if it's okay, yeah, I don't know. So it looks like he sets a flag, so it should probably be fine. Man, people, can you not format your code for real? Like, is it that difficult? Oh boy, okay. CNT, what does CNT mean? You've got A, B, and C, okay? Then you go up to N and M, you read an A. Oh, so you do reset it per row, okay. P, if it's a period, continue. If it equals this, continue, otherwise P equals 1. Okay, so if P equals 0, print B. Otherwise P equals 0. Oh my goodness. If P equals 1, do this stuff. No. Bro, I don't know. Tourist, man, I don't know how you managed to hack these people, but okay, yeah, looks like I do have a decent delta. Predicted, at least. Well, congrats to Ben Q for, it looks like, winning a MacBook Pro or something. Good job to you, or MacBook Air. I don't know if there's some prize, some computer. Apologies to Tourist for not winning, but on the bright side, you know, you got what you were looking for, right? Cool. So there you go. That's my contest. No hacks from me, but not a terrible performance. I got A through F2. That's what I was out to get. And other than losing to Anton, not bad. As far as friend standings go, pretty decent, I think. We'll see how system tests turns out. But for the moment, looks decent. Let's go over solutions now. I think that might be what's in order. So I'll go over the solutions from A through F2 in this video. So to problem A, you need to two-color this grid. So what you need is you need to make a bunch of red and white cells. So maybe you've got something like this. The thing to notice is, like, if you're going to two-color a grid, there's only one way of doing it, right? It's got to look like this. Well, I guess there are two ways of doing it. Here's the first way. And the second way is the same thing, but you just flip all the red and whites. And then it looks like this. So those are the two ways of two-coloring a grid. One very easy way of checking whether this works or not is you can say, for some position, if you look at its x-coordinate, its y-coordinate, so I'll say this is x, it increases going right, and this is y, increases going down. If you look at the x plus y, so x plus y, this value is either even or odd. Whether that's even or odd determines whether the cell will be red or white. So it's a really nice way of doing it, and you don't have to casework whether the width is even or odd. It's all very simple. So that's the idea there. Yeah, so those are the two ways. So basically, all you have to do is check, is this one impossible to do? For instance, if one of the squares that's supposed to be red was white, then this way would be impossible. You also need to check, is this way impossible? So is one of the squares that would be assigned in this color, is it wrong, right? And then if one of these isn't incorrect, then you print whichever one isn't incorrect. And that's it. So yeah. So my code for that looked like this. I have these two flags. W1 is whether way 1 is impossible, and W2 is whether way 2 is impossible. Or like whether way 1 is forced to be true or whether way 2 is forced to be true. So I iterate through all the spaces, And if it's not a period, that means there's some constraint here. So one of these things is forced to happen. And this is if W is on the even x plus y positions, then W1 is true, otherwise W2 is true. If they're both forced, they can't both be true, because there are only two ways of doing it. You have to pick one, so the answer is no. But if only one of them is forced, then the answer is yes. So it's either this way or it's this way. Yeah, so that's my solution to problem A. Let's move on to problem B. All right, histogram ugliness. So you've got some histogram with a bunch of heights. And what you can do is remove one square from the histogram for a cost of 1. And what you want to minimize is the total vertical heights of all bars minus the total heights you removed. So what you can notice here is it is possible that doing one of these operations would be very helpful, right? Let's say this is your histogram. In this case, if you remove this, then you've saved this position and this position. So you've saved 2, but for a cost of 1, right? And you can remove this 2, you can remove this, and then you can remove this. So by doing that, you've saved 4 moves. In the samples, they also do this. They also have you remove these 2. But this gives you a net change of 0, right? So it's easier for me to just not remove those. And the only time you actually gain something is when you remove a square which has emptiness on both sides of it, right? In other words, an easier way of looking at that is if you have some position in this array and the thing to its left and to its right are both smaller than it, then if you decrease this by 1, you save 1 point. So in code, what that looks like is we just read in the array. Now I make my array n plus 2 because I want to pad it with zeros. I put zeros on the 2 ends because I think that makes it easier to implement. But you don't have to. You can special case it. This is just the code that I thought would be cleanest. So I put zeros on the 2 ends. I start with a 0 and end with a 0. And then for each position, the start is like the start value. So for each position, I add the difference in heights between every adjacent position, and that's the start cost. And then the subtraction, the amount that I'm going to subtract from the answer, is if I am bigger than both my neighbors, then the amount that I can gain is the difference between me and my taller neighbor. So I just evaluate that here. So that's the idea for problem B. And that'll give you the best possible answer. All right, for problem C, yeah, so for problem C, you have 2 permutations. So this is a problem that I think something like it has come up before. It's kind of a common idea, but here's so you've got 2 permutations. Maybe the first one is 1, 2, 3, 4, and then the second one is like 1, 4, 2, 3. So now the question is, you can flip, Oh, okay. They start pairwise distinct. So you don't have 2 1s in the same column. Okay, good, good. So you have something like this. So you've got 2, 1, 4, 3 maybe. Okay, so what you can do is you can do some of these operations where each operation is you swap 2 elements in a column. You swap the 2. And you can do this as many times as you want. And then you want to know how many ways can you swap some subset of 1 or more of these columns so that after you do that, you'll have unique things in each row. Like each row will stay being a permutation. So one example is if we swap these 2 columns, then what this will look like at the end will be 2, 1, 3, 4, 1, 2, 4, 3, right? Because we just swapped this and this. Both of these don't contain any duplicates, is kind of the easier way of looking at it, or in other words, they contain all the numbers 1 through 4. So, so this is one legal way. Another thing you could do is not swap anything, and another thing you do is swap all 4 of them, or you could swap just the last 2. So in this case, there are 4 possible solutions here, so the answer would be 4. Yeah, that's the idea. So how do you actually solve this problem? So one thing to notice is that you're going to wind up with a bunch of groups, a bunch of like sets of indices where all of these indices are connected. In other words, maybe for positions 1, 7, and 10, either you need to flip all of those or you need to flip none of them. In this case, we have two groups. So positions 0 and 1 are connected, and positions 2 and 3 are connected. For each of these things, they contain unique numbers, and they're all like connected together. So we can flip this entire group, or we can flip nothing in the group. Since we have two groups, there are 2 to the 2 ways of doing that, right? We can flip white or not flip white. We can flip red or not flip red. Those are the 2 ways of doing it, 2 squared ways. Okay, so next thing, how do we find these groups? Well, it's not actually that bad. I'll use the second sample here because it's more interesting, I think. So that one looks like this. So we have 2, 6, 5, 1, 4, 3, 7, 8, and then we have 3, 8, 7, 5, 1, 2, 4, 6. So in this case, this first pair has to be in some group, right? We'll call this a red group, 2 and 3. Now, if we have a 2 on the top, we need to also have a 3 on the top. So this element needs to be there together, because if we flip this, then the 2 will go to the bottom. So whichever 2 is on the bottom needs to come to the top, and the 3 was on the top, so the 3 needs to go to the bottom. So these 2 need to be in the same group. And it turns out, when we have this, the only requirement this has is that it's in the same group as this. So this is one complete group. We can stop here. The next thing is this needs to be in some group, this 6 and this 8, right? So we have this 6. We find the other 6 on the board, so it's in this one here. And we need to connect these 2 together. There's also an 8 here, so we need to find the other 8 on the board, and we connect them. Now these 2 are connected. And then our BFS stops here, right? These are all of the things that we've needed to include. So now, again, we have the second group. So now we'll make a third group. So we have this 5. So we've got a 5 here. Now we need to include the other 5. So the other 5 is here, so we need to include this. Okay. We also need to include the other 7. So the other 7's here. We need to include this. So now we've processed this. We need to process these other 2. So now we've included the other 5. So we have both 5s, but we need to include the other 1. So we include this one here. And then we've already included the other 5. So now we've included both of these things. So now we added this to our BFS. So we need to include the other 7, which we already have over here. We also need to include the other 4, which we already have over here. So now this one here is processed. Then finally we have this. We need to include the other 1, which we have here. We need to include the other 4, which we have here. So this is processed. So as you can see, we have 3 different colors that contain all of the dominoes. And in this case, each of these are independent. So we have 2 to the 3 ways of doing it. That's the solution to that problem. What does it look like? So I just store what are the 2 indices, the index in the first permutation of each number and the index in the second permutation of each number, as far as like what things are, and then I store them as 0 to n minus 1, so I can do 0-based indices. Now this hit is like for each number, or I guess this is for each domino, have I included this domino in some group yet? So in other words, have I circled it in some color? And then if this is true, then I don't have to do a BFS from it. But if it's false, then I have to do a BFS from this domino. So if it is hit, if I've already included it, then I skip it. Otherwise, this will be the start of its own group. And then I need to do a BFS from this group. What does the BFS look like? Well, I just start at this position. I mark it as hit. And then I go through this entire array. And the 2 numbers that I need to check are the top and bottom of this domino. And I also need to match anything that matches that, like I need to look at the positions where this number occurs in both arrays. And I need to make sure both of those are in this group. So that's what this does here. I find both position, like for each of these, for both of these numbers, I find both of the positions, and then I make sure both of those are part of this group. So this is a little suboptimal, but it's definitely fast enough because it's linear time, right? So it runs fast enough. You have to use this index of to make it linear. That's an important part of the problem. And then at the end, I just do 2 to the n under mod. That's the solution. Okay, cool. That's problem C. Move on to problem D. Uh-oh. Did I fail this problem? No. Good. All right, problem D, lost tree. Yeah, so this problem is pretty cool. It's an interactive problem, and what you need to do is find some tree where what you're given is a bunch of queries, where you can say find the distance from some node to every other node in the tree. Now, you could do this for every node. If you did this query for every node, then you could find all of the neighbors, right? Because all the stuff that's distance 1, you have an edge from you to anything that's distance 1 from you. So if you do n queries, this is super easy because you just run this query for every node, and then for each node, you find all its neighbors as the result of the query, and then you just print all the edges at the end. Unfortunately, you can't do that many queries. You only get n over 2 ceiling. So if n is odd, you get n over 2 plus 1. Now, how do you do that? So one thing to notice is if you have some tree, say it looks like this maybe, a tree is two colorable. So we can color each node either red or white, like this, so that every node is connected only to nodes of the other color. So here's one way of two coloring the tree. The only other way is to flip every node in the tree. And the important thing here is that half the nodes are red, half are white. It's not necessarily a 50-50 split though, because we could have some tree that looks like this. We could have just like a special snowflake, right? These are what American trees look like. And in this case, almost all of the nodes are white. There's only one of them that's red. So if we were to like query all of the white nodes, we would be in trouble because there would be too many of them. Instead, what we can do here is if we query some node, we can tell how many nodes are the same color as it. All of the nodes that are an even distance away will be the same color. So in this case, this is distance 0 away, and all of these other white nodes are all distance 2, right? And then we'll do another example here. Let's say we query this. I guess it's pretty similar, but this is distance 0, this is distance 1, sorry, this is distance 2, excuse me, this is distance 2, and then this is distance 1, and this is distance 3. Right? So all of the even numbers are white, all the odd numbers are red. Okay, so here's how you solve this problem. So there are two cases. If there are a small enough number of white nodes, right, if the white nodes correspond to at most half of the nodes in the tree, then we'll just query all of the white nodes, and those will give us these edges like in this direction. So we'll get all of the edges going away from the white nodes. There's the other case in which the white nodes are a majority of the tree. They're over half. So in this case over here, we can't query all of the white nodes. But if the white nodes are more than half, that means the red nodes are less than half. So even though we've wasted our first query, we still have enough queries left to query all of the red nodes. And in that case, we can get all of the edges going in the other direction. So we can get something that looks like this. And then we can just ignore the first query and assume that, like, yeah, it's not really that big of an issue. Because we don't need that many queries to query all the red nodes, because they're less than half. So that's the idea. Again, to get the edges, you just look at the things that are distance 1 away from your query node, and that'll give you the edges. So cool, that's the idea. What does it look like? So you store the even count and odd count for the nodes. This is like how many nodes are the same color as node 0, how many are the opposite color. And then, yeah, I just do my query, blah, blah, blah. Oh, I also store this is edge, so I do it like a 2D array, just because I think it's easier. And then, what do I do here? Yeah, if we have few enough even nodes, then we're going to check all of the even nodes. Otherwise, we're going to check all the odd nodes. And here we check all of the even nodes except node 0, right? So then I go through all the nodes we're going to check. I query the distance from every other node to that node. And then at the end, I mark all of the edges that I've seen before. And then I print the answer at the end. So yeah, that's the solution to problem D. We're good there. Let's move on to problem E. So two more left. We've got E. I guess we have E, F1, and F2. All right, so E, lost array. So you've got this array, and you want to know what the XOR of the entire array is. But you can make these queries for you're given exactly k nodes, or you give the interactor exactly k nodes, and then the interactor will tell you what the XOR of those k nodes are. An important part of XOR, one thing to keep in mind, is that for XOR, like, everything is important, right? It's not like min or max or something, where one thing can cancel out everything else. It might be easier to think about it as like the sum, but like the sum of numbers. They're looking for the XOR, but the sum of numbers is kind of like the same thing, where just one, if you don't know one number for sure, then that one number might just really screw things up for you. So yeah, so you have to like be very careful with XOR. You can't like, yeah, it's kind of tricky, I guess, is what I'm getting at. Okay, so yeah, the problem is you have some array of size n, and you can query k numbers. You can say, give me the XOR of these k indices, and then it'll look in the array, get all of those elements for you, and then tell you the XOR of each of those elements, or like of all of those elements together. And you want to find the XOR of the entire array. So there are some cases in which it's not possible. Let's say you had a graph of an odd, let's say you had like an odd number of positions, right? So maybe you have 5 positions, and you can query the XOR between 2 elements. So you can say, what's the XOR of these 2? What's the XOR of these 2? And then you're left off with just this one. Well, if you do this, you can get the XOR of these 2, so you know the XOR of these 2 and the XOR of these 2, but you can never get the XOR of all 5. And like a good way of thinking about that is like, well, we have the XOR of both of these, but this thing, we have no idea what it is, right? Because these things could basically cancel each other out. And since there's no way of like splitting this up into reasonable groups, this winds up not really being possible. Actually, you might not even need this observation, so I'll stop talking about it. But yeah, that's like one thing. An easier way of looking at it might be, you have some nodes, right? And what our goal here is going to be is if we're able to include each node an odd number of times in the total number of queries, that would give us the right answer. So let's say we do something like this, right? So we have one query that's like that, one query that's like that, and then this has an odd number of indices, this does too, and these both have an even number of indices. So then we do one more query like this. So now every node here has an even number of edges, or it has an odd number of outgoing edges. That's not true. Okay, this is not a good, because we're not drawing edges anymore. We're drawing lines. Okay, so we have 5 nodes. So we can do 1, 2, 3. We can do 1, 2, 4, and we can do 1, 2, 5. So now in each column, this thing is picked an odd number of times, right? Everything's picked either once or 3 times. So what does that mean? That means if we take the XOR of all of these rows, these 2 will cancel each other out, and now we'll have the XOR of the entire array. That's our goal. We want to do some queries. After the queries, everything should be included an odd number of times. The logic for this is a bit tricky. There might be some construction for it, but I don't know what it is. However, you can do a DP. All that matters here is not even which elements are even or odd, just how many there are. So we need to know the number of evens and then the number of odds. And in fact, we know these both add up to n, right? So really, if we just know how many evens there are, if we just know how many evens there are, that'll tell us how many odds there are, because it's just n minus the number of evens is the number of odds. So yeah, so that's the idea. Now we need to consider all of the edges in this graph. So each thing, if we have some node which represents the number of evens and the number of odds, it can reach anything where we take some number of evens and turn them odd, take some number of odds and turn them even. Initially, you might be thinking, well, this sounds like a great thing to do with dynamic programming, but you have an issue, which is there can be cycles. And dynamic programming doesn't work well with cycles, but on the bright side, every transition is a cost of 1. So instead of doing dynamic programming on something with cycles, you can make a graph and do edges, and then find the shortest path. And that's a very similar way of doing that. So that's the idea. That's what we'll do. We'll make a graph where each node will be some possible DP state. In other words, we have some number of nodes that have been used in an even number of queries, some number of nodes that have been used in an odd number of queries. once we have this graph, if we find the shortest path from the node where we have all even, every node's been used an even number of times, to everything's been used an odd number of times, that shortest path will be the minimum number of queries we need to make every node used an odd number of times. Okay. To look at the edges in the graph, we can just say, okay, let's consider the different possible ways we could take from evens and take from odds and then add to them and get something else, right? So let's say we have like 2 evens and then 3 odds, and then let's say k equals 3. So we could make all of these odd even, so we could do 5 and 0, or we could make 2 of these odd even and 1 even odd. So that would be a -2 and then a +1. So there would be 1 odd and then, there would be 2 odds and then 1 even. Or yeah, there's other stuff you can do. I guess that's different, right? So this would be 4 and 4. Yeah, 4 and 1. Sorry, 4 and 1. And there's you can look at the other transitions as well. That's the idea. So yeah, we have the graph, and then we just have to evaluate what is the shortest path, and that tells us how we do it. Okay, what does that look like? I had some wrong ideas here that were like actually constructed. But yeah, so I store the distance to each node and where each node comes from, and then also, just for simplicity, how many odd things I changed to get to this node. And then I do my BFS. So I start with all evens, and that's my node. Everything's even, and then I want to get to everything's odd, which is node 0. So yeah, so while my BFS is empty, I brute force how many odd numbers I'm going to change, and I make sure I follow all the rules when I do that. So in particular, the number of odd numbers I change, I have to end up with a 0 or positive number of odd numbers. And then I can't ever have a negative number of even numbers either. So both things have to be reasonable. If all of those things work, then I can end up with some other number of even nodes after I flip these nodes in this way. And then I get to this node, so I basically just do the BFS. This is something you can work out on paper, but it's basically the easy way for me to consider to say, how many even nodes do you flip? How many odd nodes do you flip? After that, how many even and odd nodes are left? So yeah, that's how you do the math. And then I just reverse the path and actually do it. So this is what the code looks like. If you have any questions, you can, I guess, post a comment on the editorial or on the announcement page and just ping me and I'll answer it. So yeah. But yeah, extract the path and then follow the path, and that's the idea. For problem E, okay. 2 more parts. We've got problem F1 and problem F2. So for F1, you have a bunch of, let's talk about the problem real quick. You've got a bunch of, I think you're playing Minecraft. Seems very Minecraft inspired. Minecraft, what? You've got a bunch of sand blocks in Minecraft. Maybe they look like this. And the way it works is when some block falls, let's say we have this block, we're gonna punch this block or something. What will happen is it'll fall all the way to the ground, and any blocks that are in any of these positions, or possibly this position, all of those will also fall. So this one will fall, and then like it'll hit this node here, right? When it hits this, that will hit it'll update all of these nodes. Right, and then it'll hit this node. So then this node will do this in yellow maybe. This one will update all of these. And all those will fall. So in total, all of these blocks will fall. And then the question is, how many, for F1, how many blocks do you have to punch so that every node ends up falling? In this case, you only have to punch 1. So if we punch this node, this will fall to the ground. That'll also, when it's over here, it'll update this node, so this will fall to the ground. That'll obviously update all of these 3, and then when this node's over here, it'll update this one. So if we punch just this node, it'll hit everything. If you know strongly connected components, this is a great use case for it. So using strongly connected components, we can identify some things about this graph. Any group like this is strongly connected. We'll call it strongly connected if you punch any node in the group, every node will fall, right? So any node here we can say like it can reach other nodes through things that would make fall. This one would make this one fall, this one would make this one fall, and this one would fall back to this one, right? So we have this cycle, so no matter which one you punch, they'll all fall. This is like one connected component, so we can imagine making this like its own group. And then this is also a group, and this is also a group. So once we've made these maximal groups, we also have this thing called a strongly connected component graph, right? So we turn each of these into nodes, and then each node can like link to other nodes as the ones that it has edges to. Now, an important thing to notice is there are no cycles in this graph, because if you have a cycle like this, then this whole thing is one strongly connected component. So this would all be one node. So an important property here is that we have no cycles. We've gotten rid of all the cycles here. So maybe it looks like this, though. Maybe we have something that looks like this. Maybe we have another red node over here. And then the graph would look like this. So if you look at the yellow graph, that's our new SCC graph. So in this case, we would have to punch this node here and this node here. In other words, we need to punch all of the SCC nodes that have an in-degree of 0. Right? Both of these have nothing going toward it. Anything with an in-degree of 0, if we punch it, there we go. If it has a positive in-degree, what that means is that if you knock something else, that'll end up knocking this. We know there are no cycles. Cycles would break this, right? But we know there are no cycles because it's a strongly connected component graph. So yeah, that's the general solution. One other solution detail, which I'd like to cover, is how do you build this strongly connected component graph in a way that it doesn't have that many edges? So if you're looking at some block, we want to add a constant number of edges for this block in order for our strongly connected component code to run quickly. What we can do is we can add an edge to the first thing we see going down on the bottom below it, the first thing we see over here, the first thing we see over here, and then possibly the item immediately above it. So for each position in the graph, each position in the grid, we add up to 4 edges maximally. And then we know we might hit a bunch of things below us, right? But we have this element here. He will add an edge below him. So we'll have this like transitive edge, which means we'll be able to reach this. So it'll count as if we have an edge directly to it, but we don't actually have to add that, right? And strongly connected components will just take care of it for us. So that's the idea. I'm not going to go through the strongly connected component code because it's a mess. But I guess I changed my solution quite a bit. So look here. But here's the idea. So we read in the graph, and then we have the strongly connected component code. We add an edge to the things below us, if there is something below us. And then since I'm going like left to right along a row, if there's something below or equal to us on the left, we add an edge to that. If there's something directly to us to the right, we add an edge to that. Otherwise, if there's something below us to the right, we add an edge to that. So this like handles how I'm updating this top in X part. And then if there's something above us, we add an edge to that. So that's the idea behind this solution. I'll zoom in a little bit so you can, I guess, look at it a bit more clearly, maybe. So there's how you add the edges. And then after that, I just count the number of things which have no in degree. Right? So I build the compressed SCC tree, check the things with no in degree, and then that's the answer to F1. So F1 is pretty easy if you know SCCs. F2 is a bit more tricky, and I'll do my best to talk about it, but it's a bit messy. So there are a couple observations here. The first one is that this is not a general graph. This graph that we're building has very specific, important characteristics. The most important is if you have some node, it can reach everything below it, right? And if this is the top node in some row, nothing can go across this. Like, you can never have some edge that goes like this. This is never possible. Because if you have some node over here to the left, it can't reach to the right without you being able to reach something to the right. Because it would need, like, in order for it to do that, you would need a node here somehow, right? You could go up, maybe reach a node here, and then this node would reach over here, right? But in this case, you have this path as well. So the important thing here is that if we look at these SCCs that have no in degree, the ones we were counting for F1, if we look at those SCCs, sorry, I'm covering this, but if we look at the SCCs on the top, right, the ones with no in degree, those ones are, we can sort them by X, and now they're like in a very important order. In particular, any node in the entire board here, the SCCs that can reach it, of the SCCs on the top, right, that will be a continuous range of SCCs on the top. So it'll be like from here, all the SCCs can reach it, and then after here, this one can't, all of these ones can't reach it, and then all the ones before this can't either. It might just be one SCC in this range, but it's a continuous range. Yeah, okay, so then what else? What do we do from here? Well, basically, we're going to find this range. So since we have some SCC graph, we have an SCC graph like this, what we'll do is process it, we'll reverse all these edges, and then we'll process it kind of in reverse order. And then as we do this, we want to say for each node, what is the leftmost and rightmost top level SCC that this node can reach? We can do this in linear time by, if we process this in topological order, right? So in other words, like you can think about it from bottom to top, but really the way you sort them is in top sort order of this graph, right? So we would process this one, and then this one, and then this one, and then this one. That way the things you look at are always processed before you, or you could do a DP and then do it recursively, but I was worried about time. So yeah, okay, so you look at the stuff that you can reach, and of those, the leftmost thing you can reach is the leftmost thing of all of the people you can reach, or the rightmost thing of all the people you can reach, unless you are a top SCC, in which case, by definition, you have no in degree, right? Because we define the top SCCs to be the things where nothing can reach them. So you have to knock them to kill them. All right, so now we know for every node in the graph, what is the leftmost and rightmost thing that this node can reach. The leftmost and rightmost top level SCC this node can reach. Or sorry, the leftmost and rightmost top SCC that can reach this node, right? So where if you knocked that node down, it would hit a bunch of sand blocks and end up hitting you. That's going to be some continuous range of top level SCCs. Okay, we have that part. Now, the last part is just like a pretty simple observation. When they say you have some column, right? In this column, you need 3 elements to be knocked down. We have a sand block here, 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 and here. That's equivalent to just saying this sand block needs to be knocked down, right? Just worry about this one. If you knock this down, all of these will be knocked down. If you knock anything above it down, this will be knocked down, right? So just worry about this one sand block. Everything else will handle itself. Nice and easy, okay? So, yeah. So now, each node, this one says like, okay, the SCCs that can reach me are these SCCs here, right? Each node has some continuous range of SCCs that can reach it. And you have order n nodes where it's like, okay, here are the SCCs that are of importance. You've got several of those. And now you just need to know what is the fewest number of top level SCCs that you need to pick so that you pick at least one SCC in every range, right? So you have like maybe this range here, you have maybe this range here, you've got maybe this node here has this range here. So what these ranges look like is something like this. So you have some ranges. So now you need to pick some of these top level SCCs, maybe pick that one and this one. And in this case, we have cut each of these at least once. Now, this is a problem that I've talked about before on this channel called gassing bunnies. And I'm going to do an algorithms thread episode on this because it's so common. It's a very important idea. But yeah, this is gassing bunnies. So in gassing bunnies, we have a bunch of ranges, right? And we need to kill the fewest number of positions so that we kill every range at least once. And the solution to this is just sort by right endpoint and then kill when you have to, right? So in other words, wait to kill the bunnies for as long as possible until some bunny would be about to escape. So when I say bunnies, I mean like in this range, this is like some bunny. So the bunny will enter your train here and leave your train here, right? So we need to kill the bunnies on the train sometime in one of these positions, right? We need to gas them with poisonous gas sometime in one of these positions. And so you need to gas somewhere in one of these positions and somewhere in one of these positions. So here, if you gas right here, right before these bunnies were to leave the train, then you'll get all of these, but you'll also get all of these ones for free. So yeah, solution to that is you sort by right endpoint, and then if some bunny is about to escape, then you kill it right then. So that's the solution to F2. We still do the same part with the SECs, so all that part's the same. But then we do this BFS to see what is the leftmost top SEC and rightmost top SEC each thing can reach. So we do that. We do this BFS, right? This is just what I mentioned earlier. And then we get all of our bunny ranges. So for each element that's like some requirement, right? We walk up, we find the requirement. If this is the requirement node, right? This is the node that needs to be knocked down in this X coordinate. We build the bunny range for this node. Okay, so now we have all these bunny ranges, and now we are solving the gassing bunnies problem. We're not solving this problem here. We've made a simpler problem, and this is the gassing bunnies. So we have all these bunny ranges, and when we look at this bunny range, we store the last time we've killed all of the ranges. And if we've already killed this range, then we can skip it, right? But if we haven't killed this range, since these are sorted by right endpoint, we need to kill the range right here. Because if we don't, these bunnies will escape. Okay, that's the solution to problem F2. And that's all I've got. Let's see, did I pass the problems? Who knows? System testing is still running. Okay, so I'm not gonna make you wait forever because it looks like it's taken a bit. 69%, there you go. We'll leave it at that. Looks like I did pretty well today. So I'm happy with my performance. I may have gotten international grandmaster back, which is always fun, always fun. I'm a little worried about time on problem E, but we should be fine. We'll see. I guess we'll see. I don't know. Maybe we're not fine. We'll see. Thanks for watching. Have a great day, and hope you enjoyed the contest as much as I did. And thanks to the Canadians for making this one. This is one of the few Canadian contests out there. So thank you very much. All right. Have a great day, and good luck, have fun on the next contest you do. Goodbye.